everyone. I'm Andreas, teaching at UT Arlington, and I'm a structural engineer. So I was brought here, or when we're discussing what I'm going to talk about, to give a crash course on structural engineering. So we're going to touch on many things, but mainly touch. So if you have more questions, or let me know, we can discuss it on a break or later in the day. But I promise there are no equations here, so it's just pictures and discussion. So,
it's the curve, huh?
Where? Oh, here? Oh, okay.
You should use that right there. I don't know why that's not working. It has the laser pointer works, but go ahead.
I see.
Hit that area.
Okay. So, brief outline. It has a bunch of topics. First of all, structural engineers, what do we need them, why they're around. Then a few things about materials. The focus here is on masonry and the role that it can have in a structure, whether it takes loads, doesn't take load, how it's being loaded. I will briefly touch on the codes that we're using and the loads that they discuss. And then at the end, I will talk about the load paths that we have to be careful when we design a structure or we assess a structure, make sure that we can safely transfer every load to the ground. And when that doesn't happen, what's the cause? What are the failure mechanisms for this type of structures? So why do we need structural engineers? Instead of going over and over what we can do, I'll show a picture of what happens if we don't have them. So that's how the world would be if structural engineers were not around to build a bridge. And now, getting a little bit more serious. So what do engineers do? They analyze and they design structures. And by structures, this can be bridges, buildings, dams, offshore structures, tunnels, towers. And when we analyze them, we have always to consider specific load scenarios. So we have to find what the loads are, either through investigation we do, or typically these are found in the codes, and we'll discuss them later on. So we have to identify the loads that come from the building itself. It can come from the people who walk or use them, and it can also be wind, rain, flood, earthquake, and these are extreme scenarios, blasts. So this is our goal. This is what we do. Now, what are the considerations? There are 4 major considerations that play an important role when we analyze and design any structure. If I have to pick one, that's safety. So we care about aesthetics, we care about cost, but the very first goal we have is we have to make sure it's safe. Then we also care about the serviceability. So we have to, it might be safe to walk, but if you start, if there are vibrations there, that, or if you work in a building, a high-rise building that sways back and forth, and it gives you a headache, then okay, it's safe, but you cannot really use it. So it has to be serviceable. Then it has to be economic. We're part of the society. We know that we have to save as much money as we can. So it's not that we will spend endless amounts of money to build whatever we want. And then, lastly, it's good, whatever we build, to be aesthetically pleasing. It's not our top priority, but for sure we need to take care of that and work with architects that have a better idea about this and ensure that our buildings and structure will look good. So, basic of structural engineering. As we said, it's analysis and design. So the analysis part is what we do with computers these days, and the goal here is we have to determine the loads, identify the loads that will be applied on the structure, and determine how the structure will respond to this load. So that's the first part that we do, and once we have the loads and we know what the deformations will be and the stresses in the buildings, in any structure, we have to come up with a structural design. So the design is we have to give dimensions to members. We have to identify the materials to make sure that we can safely transfer the loads we have identified. So we typically, in a school, we teach our students to design new structures. So the path to designing a new structure is essentially you assume a preliminary design, you come up with a structural model for that, so we simplify things, we keep only the structural elements, the non-structural elements are only included in the simplified model as loads. And then we apply these loads, and the goal here is to obtain the reactions, make sure that we can take the loads in the foundation, and also find all the forces in the members, whether these are beams, walls, columns, braces. And then given these loads, you have to check for every single element, every single structural element, that it can survive the stresses in terms of tension, compression, shear, and bending. And then once we do the members, we have to make sure that when they come together, all their connections are also safe. And if all that falls into place and we have an economic design, we'll go ahead and produce the drawings. If the design is not economical, or if we have members that cannot, that are unrealistically big to take the loads, then we have to go back to the drawing board, come up with a different design, and start from scratch. Now, this procedure obviously gets modified when we're dealing with existing structures. So with existing structures, the structure is there. We don't have to assume a design. We don't have to assume anything. We have to figure out with as much detail as we can of what we're dealing with. So we have to estimate if there's reinforcement or not. Sometimes you walk in front of a wall and you don't know what's behind it or what's inside it. And that's a big problem that we're having. And that's why we have experts that they're going to tell us later in the day how you approach that. Because it's very important to know what the structure is. And sometimes with older structures, with historic structures, they're not drawings. I mean, I had to deal with a structure, or a couple of structures in California, and all you get is what you can see. There's nothing more to that than that. So once we walk around the structure, get as much information as we can, again, then the next step is similar. We have to come up with a structural model. We simplify things as much as we can so that we save some work. And then we follow the codes. We estimate the loads that these structures will see, and that's how we get all the forces and the stresses in the members. Again, we go through the same procedure for every member that we have. We have to make sure that it can take the combination of stresses, and then we have to go through every single joint. And if all that works out and we satisfy a good factor of safety, we're good to go. The structure is okay. However, it's often the case that as our knowledge evolves, that the structures tend to be unsafe with current standards. So what do we do then? Our first option is we have to repair and retrofit, and that's what we try to do, especially with historic structures. However, sometimes that's not economic. In that case, it gets demolished. Hopefully, it's not that often. So an important thing here is that as structural engineers, we really believe that we can fix anything. The question is at what cost that can be done. So if endless amount of money is available, sure, we can do it. However, does it make sense? That's a question that we often have to answer. Now, the next step is the building materials. I'm sure you know them, you see them around. When you walk, there are mainly 4 types of materials. So, wood, of course, and then concrete and steel. However, here we're focusing on masonry. And masonry, it can have very different types of masonry units. So we have the clay bricks. I'm sure you know them. We walked around campus today. Most of the buildings on the exterior have clay masonry units. Then you have the concrete units that have been developed lately, and they're used a lot, and especially for when the load demands are high, because we can reinforce those. And then we also have glass units if we care about the appearance. Also stone, that was probably one of the oldest ways to do it. And you can see that this is a picture from Greece. By the way, I'm Greek. I grew up there, so I'm a little bit biased. And here you can see Acropolis. That's very famous. We're very proud of that. It was built 25 centuries ago. And here you can see it's masonry. So this is a beam, and it's essentially a stone masonry beam. And also we have ice. I mean, you see the igloos. They're made of ice. And now that's a modern version of masonry in San Francisco, where you say it's all glass. Now, the basic structural elements, how we identify them. So once we go into a structure, we have to see what are the members that take the forces. That's a very big step before we start talking about whether a structure is safe or it has damage or anything. So we have to identify the role of each element. So we have elements that are only loaded axially and in tension. These are usually braces or tie rods, that are very commonly used to glue things together for diaphragms and parapets in masonry. Then we have the members that are loaded axially in compression. I'm sure you know them. These are usually columns. And the braces, again, if they're designed correctly, they can take some compression. Then we have members that they can take a combination of bending and shear. Usually these are the beams that run horizontally. And finally, we also have members that can take axial high compression, and then also, and they have very high stiffness. And these are walls. They can, and here is an example. And masonry usually works with that. So you will never see a brace made out of masonry. That doesn't exist. But we might use braces to retrofit or strengthen a masonry building. Then we go to the structural systems. What systems do we have around? So one of that you see quite often for roofs in stadiums and train stations, or areas where you have a big span that we need to cover. These are trusses. Then we have systems that have beams and columns at most steel and concrete buildings, and these are, we call them frames. And then finally we have systems that are loaded directly in compression, and this is where masonry was used from the ancient times. So these can be load-bearing walls and also arches, like the one you see, that some of them have a life of over 3,000 or 4,000 years. And you can see the arches are very smart structural system, where it's very pleasing to see. It looks really nice, and it only takes compressive forces. So we have the loads applied on the top, and then these are transferred around the arch to the pillar. Now, other structural systems that are important to identify is what we call plates and cells. And examples for that can be the diaphragms. I mean, the place where I'm standing on here, that can be considered a plate. So it's a big area, in two-dimensional area that takes load perpendicular to it. And here we have a schematic that shows how this works. So this would be the diaphragm that holds the walls together, and its role is very, very critical in these structures. And let's say that you have high winds, so you would have this wall that is loaded with the wind, and that's load that we call it out of plane load. And for the wall in what color is that? We have the load of the wind will be an in-plane load. So that wall would be loaded inside its plane. It would deform along its two big dimensions. However, the wall loaded out of plane, you will see that it's loaded and tends to tilt, and it's along its weak axis. So we really have to be careful about this type of walls. And then you can see that masonry can be even used for diaphragms, and that's how structures in the past used to be built. Now, what are the possible roles that masonry can have in a structure? It can work, whether it's reinforced or unreinforced, it can work as a bearing wall, and it can take lots of gravity load, and it can work as a shear wall, especially if it's reinforced. Then it can be a non-structural element. And as non-structural elements, we usually consider the veneers, that's the facades or on the exterior of the buildings, because it really looks nice. The aesthetics of a masonry wall the looks are very good. And then it's also used a lot, especially here in Texas, for fences. It's really nice to see. And then we have a category right in between that I studied quite a bit during my PhD, and that's when we use masonry as an infill wall. So we really have a frame around it that can be made out of concrete or steel, and then we have a masonry wall between the columns and beams of that frame. So usually for all the structures that were built in the 20s or even earlier, and there are lots of them in California and also around the world, you see people designing the frame without accounting for the masonry. So they design as if the masonry is not there. Turns out that the masonry, not only it's there, but it really makes a difference on the behavior. And that's something that people didn't understand until very recently. So some examples to see. Here are some masonry fences. Then you can change the colors, the schemes, to make it architecturally pleasing. But in all cases, here's a schematic of how this should be designed and built properly. So there has to be a drilled pier, and then we put some reinforcement. There are some typical dimensions on that, and then we built the posts and the panel. And it's very important that we have the reinforcement there at the post, because that is going to take all the wind load, all the pressure because of the wind. Otherwise, it's very common. You can see these structures falling apart. Then we have masonry veneers. Again, we said it's non-structural. We put them outside of structures built for reinforced masonry or wood. And here we have a video, I believe. Oh.
You right-click here, and then we'll end the show. Yeah.
Okay.
And then we'll come in here. You want to do this one?
No, it's this guy. So again, So as I said before, I was in California and they're really worried about earthquakes. So this is a structure that we tested, and we tried different connections around the structure to check how they behave in the earthquake. So here, as you can see, that side did very well. However, if you to see the other end of it, you see that we had that connection didn't work very well. It actually didn't work. It was pretty bad. You see that we got the initial crack grew larger and larger, and this was about to come out. So was that dangerous for the safety of the structure? The structure was okay, but if someone was to walk around it, there's a very good chance that this might fall, and that's a falling hazard. That's very, very dangerous. So that's a bad example. So we learned a lot out from that test. Then another test we did was a reinforced masonry structure, and We also tested that quite hard. And focus on what's happening on the bottom story. You see that? These are reinforced masonry shear walls, and there's lots of reinforcement, way more than what we would use in a structure in Texas. And you will see that this middle wall, all the reinforcement fractured, as we figure out later, and it just slides back and forth on the foundation, while these two T-walls at the end of the structure, they develop big shear cracks that are very dangerous for the building. But again, the outcome here is that despite all the damage, the structure holds up very well. And that, as we will discuss later, has to do with the redundancy. So we, as engineers, we provide alternative load paths. So if something fails, the structure will reconfigure itself and its path, the load path, so that we can transfer the loads to the ground. But that, of course, up to a point. So that would be a structural drawing of that structure, and this is how an analysis model would look like. So we would very carefully substitute each wall with a line element that has all the properties. You see all these different width and color elements that represent different material properties and different sections, so that we can get a good model and good representation of the structural behavior. Then that would be an infill frame, like the one I discussed before. You see that's a frame I designed based on the practice in California in the 1920s. And at that time, they never considered earthquakes, they never considered lateral loads. That would be the design. It's very inadequate compared to current standards. That's how the structure would look like. And that would be a simplified model, because as we said, engineers tend to simplify things. So we would substitute its infill wall, infill panel, with two diagonal struts. And if we're to see the behavior, here you will see why it's important to account for masonry, even if it's ignored during the design. So that's one of the last tests we did on that structure, and see what happens on that bottom panel. Doesn't look good, right? And that's my last video. That's a close-up of that column. So this is the wall that you saw falling apart, and this is a concrete column next to it. And this is not to tell you that an earthquake is to occur here in Brownsville, but I really want to point out how in a building things work together. So it's not that we can just ignore masonry or parts of the building, saying that that's not going to take any load. We really have to consider the behavior as a whole, no matter what the load is. And here you'll see why. So there was a shear crack that developed in the infill, and that propagated through the column and really tear the column apart. and the structure would have collapsed if it hadn't been for the 2 steel towers that you saw before that were holding the structure. I mean, we didn't have any safety at that point. And we even lost the camera. Yeah, that's it. Okay, so back to our presentation. So, building codes. The very first one was found the 18th century before Christ, and that was in Mesopotamia, what's currently Iran and Iraq. And at that time, they had very good masonry construction going on. I mean, they still have structures around that were built in the era. And the code was very simple. If a house was to collapse and kill a member of the family of the owner, equivalent member of the family of the engineer would have to be killed. So it was very simple, no calculations, nothing. Make sure it stands. That's the point. So, of course, as time went by, we developed better codes, more reliable and more informative. However, in the US, it's interesting, especially for someone coming from abroad, that there's no national building code. So, and the code development in this country is actually quite perplexing for me. I'm sure Ben understands it and knows it very well, but that doesn't apply to all of us. So here you have technical organizations that they develop provisions, and then there are the model codes that they reference those provisions, and then you have the local authorities that they can select and adopt the codes that they like. So it's very, as I said, complex, but that's how it works. And then what we really need to keep in mind is that formulas do change. It's not that if someone learns a code, and that's a very big message that I stress out I point out for my students, it's not that you learn the code now and you will be using that throughout your life. I mean, every 3 or 5 years they have cycles, and they update the equations, they update the procedures, they have different design methods, so someone needs to be updated, and you have to keep pace with what happens. So for the loads that the structure builds, we have what we call ASC 7, and the current version was from 2010. So it's ASC 710 that we currently use. And this defines the minimum loads for buildings and any other structure that you might think of. Then we have the design codes. So the design codes, these are put together by specialists and engineers, and these define the requirements to design for a particular class of structures. So if you have a concrete structure, you're going to use what American Concrete Institute 318 provides. If you have a steel structure, you go with AISCE. Bridge, ASTO. And that's how the concrete document looks like. Now, when it comes to masonry, we have what we call MSJC, which stands for Masonry Standards Joint Committee. This is how the document looks like. The MSJC, I think Ben is part of it, has a cycle right now that updates every 3 years. And it has a very detailed procedure on how things change. So there are ballots, people vote, and then whatever changes, it has to be approved by ACI, that's the Concrete Institute, and also TMS, that's the Masonry Society. And also then that's open to public for comments, and the committee has to address the comments before the code is, before MSJC is approved. So going to the loads now, what type of loads do we have? We have the dead loads, the live loads, other loads, and then we also have the temporary construction loads, and that mainly applies to bridges when we have to cantilever out a part of the bridge. Now, the dead load is essentially the weight of the element itself. So if you have a roof, you have to account for its weight. And then it's also whatever objects will be permanently attached to the structure. So that's plumbing, toppings, partition walls, all that's considered, whether they take any loads or they don't they don't take any loads, they create loads. They're loads themselves, so they have to be accounted for. Then we also have the live loads. And these are loads that are temporarily adjusted. That's for an auditorium like that, the designer had to assume a capacity because that and design for that. So humans are considered live loads. They come and go. Then cars in a parking structure, they would also be considered live loads. They're there one day, they're not there another day. And then you can use ASC 710 to get that. Then the other type of loads, you can have snow, wind, flood, blast, earthquake, and there are provisions to calculate the loads for that. So it might look funny that mentioning snow or earthquake here in Brownsville, but you will actually see that there are maps in that document that give you a load. That's usually very low, and the design would be governed by the wind in this case. That would change in California. But people need to be aware of that. So when we go to the live loads, we have to calculate the tributary area. So if we want to design this beam, we have to find the area that will load, that any load on the area will load the beam. So this would be the answer for the beam B. If you want to do column C3, then this would be the area that will load the column. Then going quickly to the snow loads, you see there is a map. It tells you which areas. I mean, I'm sure Colorado is way higher than Brownsville. Brownsville is probably not loaded by snow, but right, it's probably zero. And again, there are provisions to see how this you can calculate. Then you go to wind. That's very important here in Texas. So you can calculate the wind speeds, and there are formulas to translate that into load on the structure. And that's what you will need to do in order to assess a building here in Brownsville. And there are a number of factors that are taken into consideration. Then we go to earthquakes. You see, it's negligible, but it's there. I mean, nobody can rule out the chance of having an earthquake. It's not going to happen tomorrow, and it's not going to be big, most probably. But this works with probabilities. I mean, if you remember about a year and a half ago, we had an earthquake in Oklahoma, or there was one in Virginia two years ago. So especially with all the drilling going on in the area, you cannot rule that out. And again, it's not going to be as bad as it was in Japan or California, but it's something that the code needs to address. And then what's important for earthquakes is that the forces on the structure are proportional to the mass of the structure. So, and masonry structures have this disadvantage. So they're heavy structures, so they attract the earthquake loads. If you have one-story or three-story building out of masonry and out of wood next to each other, the masonry one will attract much higher forces. It probably has higher strength as well, but the forces it's going to see are much higher than what the wood is going to see, just because of the difference in mass. Then here, we also have the load combinations, and these are from ASC 2000, ASC 7 of 2010, and you can note, if you remember the previous version of 2005, that these load combinations, the coefficients have changed, but they have also changed the actual load themselves. So it used to be 1.6 times the wind, for instance. Now it's 1 times the wind, but the wind itself changed. So at the end, it comes down to being essentially the same load. But you need to be careful when you calculate this. I mean, for instance, in my class, I was teaching masonry last semester, and students got this load combination with the calculation of wind from the previous document. So that's inconsistent, and that can lead to trouble because you really underestimate the load. So you have to pick a document, usually the latest one, and follow it throughout in calculating the loads and also calculating the factors that will be applied there. Then we go to the load resistance of masonry. So masonry can provide very high strength and stiffness in shear, in compression and shear. So you can compress it as much as you want. I mean, okay, at some point it will break, but usually it breaks at way higher loads than what it is. Masonry structures are typically loaded at around, let's say 10, 20 would be an exaggeration, percent of their actual strength. So they have a lot of safety in terms of compression and a lot of capacity. In terms of tension, though, they're very weak. I mean, they have some, but it's negligible. And actually, codes just ignore it. You assume that there's not tensile capacity because it's very easy. They have these joints that are planes of weakness, and they can very easily crack. And that's a big disadvantage for masonry if it's unreinforced. That's why we tend to put reinforcement there so that the reinforcing bars can take the tensile loads. And what we need to take into account is that the failure of masonry is very brittle. With design terms, we want, based on the knowledge we have the last decade or a couple of decades, we want our structures, if they fail, to do it in a very ductile manner. So that means that they can deform a lot to give us a warning before they collapse. Masonry structures, they don't do that. They don't do us that favor. They don't deform that much, but suddenly they develop big cracks and then they're gone, or they can be gone. So we have to be very careful with masonry structure when assessing how they're doing. Then the resistance. What is important to know in masonry is that the weight it carries, it's actually a good thing. In most cases, the resistance of the masonry really depends on the load it carries. So if someone is to remove the load from the top of the masonry, thinking that, okay, I reduce the demand, that's not the right path. That's not usually, because masonry has a lot of capacity in compression. So, and if you compress it, you make it sturdier, as opposed to just leaving it loose. Then it's much easier to fall apart because the arching action that goes away. The shear resistance drops because resistance depends on cohesion and friction. So if you reduce the vertical load, the frictional resistance decreases as well. And then you can see that we use reinforcement. That's really to account for the deficiency in taking tension. And then we also use mechanical anchors. That's also another tool that we have as engineers to make sure that we glue things together. Then what's important for every structure, if you're to assess an existing structure or design a new one, is make sure there's a very clear and strong load path provided. So we want to make sure that every load, that whether it's gravity, so that's vertical, lateral, wind, earthquake, or whatever, it has a clear path to go to reach the ground, and then we're good, we're safe. And I mean, as long as the foundation is also good. And what is very important to keep in mind, especially when we start combining different materials, is that the loads get attracted by the stiff elements. So if you have wood and masonry next to each other, and you're to load them, masonry is way stiffer, so it's going to carry most of the load. I mean, it's like having two springs, one soft one and a stiff one. If you try to push them together, the resistance you're going to get will be from the stiff one. That's what is going to carry the load. The flexible one can move like that. So in our structures, with masonry is that stiff spring that takes the load. So we have to be very careful. And what works in our favor is that usually they come with high strength as long as it's compression. If it's tension, it's when the problem starts. And then a typical load path for any structure, for any building, is that we have the gravity loads that are carried initially by diaphragms. I mean, the place where I'm working on, we can consider it a diaphragm. So my load will be taken by this wooden surface. It will be carried horizontally to probably some beams that run either way on the surface, or girders or joists, whatever they can be, or you want to call them. And then from there, they would go around where there's probably a wall, or there's some columns that are along this surface. And then they go down to the foundation. And that's a small example. Any structure around, you see, that's typically the path. And then, what happens when we go into a building is that we see especially from all the tests that we did, that the structures have a great ability that works on our favor. Especially older structures, they have ability to redirect the stresses. So the stress fields get changed once we have a crack or once we have some damage, and that's due to the structural indeterminacy. I mean, if this is your structure and that's a simple cantilever, and you tip it, it goes. When we build structural engineers, we never rely on a single way to transfer the loads. So in real structure, we would have at least a brace on this side, so even if this is to fail, the brace will take the force. Or it might be a frame that we will make sure that we can take the loads. Or in masonry, same thing. You will see cracks and you will see stresses moving around the crack so that they can reach the ground. But again, we know that ability of the structure is there. We don't want to abuse it. That's important to keep in mind. And then what's also important is a structure that has cracks is not obsolete. We don't tear it apart. I mean, we have to assess it carefully, see whether it can provide the load resistance that we want. And now, finally, I have a couple of slides on what are the typical failure modes of masonry. And that's usually cracks. So as we said, these are created because of tension, usually, and you can often see your structure cracking. And that can be because of loads, or it can be because of the concrete masonry, for instance, it shrinks. So you might have shrinkage cracks. Or the brick masonry, it absorbs water and it tends to expand. That doesn't apply for older masonry structures, because at that time, after they got the brick from the oven, they would let it sit for a while. So it would absorb the moisture, it would become bigger, and then it would go on a structure. Now this route has been accelerated, so it would go on the structure and then absorb the water. So these are things that we need to take into account. And we have the expansion joints, that this is the very first line of defense we have against this type of cracks. Now, other cracks that we might have are cracks because of loads. Somehow we have lateral load here, you might have something leaning against the wall, or it could be an earthquake or a wind, and you might have this step-like crack. Or this is the crack I was talking about from the shrinkage. And what's more common probably is that cracks in masonry are because of differential settlements of the foundation. So if you have a foundation that expands and moves upward, it will create a crack at the top. Or if it goes down and you have a solid wall, it will have a crack at the bottom. Or if you have openings, you will get cracks around the windows. And in most cases, real structures tend to start cracking around windows if they have so. But again, that's not something to worry us. As long as you get an expert like the ones we have here, you can identify what's going on and fix it. So with that, I'd like to thank you and pass it on to Ben.